We're going to go through the 17.2, the equilibrium law homework for you, in which problem number 23, the dissociation of hydrogen iodide into its elements takes place in a 1.0 decimeter cubed container at 440 degrees Celsius. When 1 mole of hydrogen iodide is used, it is found to have decreased to 0.78 moles at equilibrium. A. Calculate the equilibrium constant for this reaction at this temperature. First step, write the reaction. So we have HI dissociates into its elements H2 and I2. Balance it, so we have 2HI makes H2 and I2. We need to figure out our initial, our change in concentration, and our equilibrium concentration. We know we are starting with 1.0 moles of hydrogen iodide and 0 moles of hydrogen and iodine because they are products. We also know that we end with 0.78 moles of hydrogen iodide at equilibrium. Therefore, we need to go back and fill in all our information. 1.0 to 0.78 is a change of 0.22. Because there are 2 of them, we need, and I'm going to go back and fix this, because there are 2 of them, we are losing 2 times 0.11, since the loss is 0.22. That means we are adding 0.11 plus 0.11 of each of our products to give us those equilibrium. Now we want to calculate the equilibrium constant. So we need to write the equilibrium expression. Kc equals products over reactants, and use any coefficient as the exponent. Let's input the information. So we have 0.11 times 0.11, which is also 0.11 squared, over 0.78 squared. Plug that into your calculator. You get 0.01988. Turn that into a cleaner number, 1.99 times 10 to the negative 2. We need no units for the Kc calculation because it's just a representation. So this is telling us that reactants are being favored. If you needed the units for the equilibrium concentrations, remember the units for concentrations is moles per decimeter cubed. B. Deduce whether the dissociation reaction is endothermic or exothermic, given that at 600 degrees Celsius the value of Kc is 0.04. So we know if we increase temperature and we increase Kc, and increasing Kc means we're favoring the products. That means the forward direction has to be an endothermic process. Sorry for the spelling. So we are an endothermic process because we have a higher Kc and those Kc are products. When we increase temperature for an endothermic process, you are favoring that direction. Since we are increasing the value of Kc, we are increasing the direction of the products. 24. The reaction is carried out in a closed container with the initial concentrations of both reactants at 1.6 moles per decimeter cubed. Kc for the reaction is 1.7 times 10 to the negative 3. Calculate the concentration of NO at equilibrium. So step 1, I'm going to rewrite the reaction so I can write stuff underneath it. Then I need to identify my initial concentration, my final or my change in concentration, and my concentration at equilibrium. I'm starting with 1.6 for each of my reactants and 0.0 for my product. Now, because I don't know anything else, I'm setting everything equal to x. So I have minus x for each of my reactants because I'm subtracting that change. And then I'm plusing 2x for my product because I have 2 of them in the balanced reaction. Now I'm going to go through and put 1.6 minus x, 1.6 minus x, plus 2x. Now because our Kc value is incredibly small, that means we favor the reactants and the reaction barely starts. Therefore, we can assume that the concentration at equilibrium for our reactants is the same as its initial concentration. Therefore, these both are 1.6. Let's set up our equilibrium expression of products over reactants. Let's substitute in our given information. So we have 1.7 times 10 to the negative 3 equals 2x squared over 1.6 times 1.6 is 1.6 squared. So I'm going to multiply 1.7 times 10 to the negative 3 times 1.6 squared. That gives you 0.004352 equals 4x squared because I distributed that squared value. Divide by 4, I get 0.001088 equals x squared. Square root it, I get 0.033 equals x. I want to know the concentration of NO. Therefore, I have 2x, which is so 2 times 0.033 gives us 0.066 moles per decimeter cubed. And that is the answer in which we are looking for. Sorry for the way in which this problem is being represented. It did not copy over very well. But 25. The production of ammonia is an important industrial process. The reaction used in the production of ammonia is an equilibrium reaction. Outline the characteristics of a system at equilibrium. So this was back in 7.1, what determines an equilibrium state. So there were 5 things in which we had talked about. One was the macroscopic properties. These remain constant because at equilibrium we can see no change in those macroscopic properties. It looks like the reaction is done even though it's not. The concentrations remain constant. Even though it's dynamic, reactants are becoming products are becoming reactants, the concentration does not change. The forward and reverse reaction rates are the same as well. And those are just 3 examples in which equilibrium, or which represents equilibrium. Deduce the equilibrium constant expression Kc for the production of ammonia. So Kc equals products over reactants. All right, so these are both the other parts of this problem. So I'll be working through these and then each individually. Looking at 0.20 moles of N2 and 0.02 moles of H2 were allowed to reach equilibrium in a 1 decimeter cubed closed container. At equilibrium, the concentration of NH3 was 0.060 moles per decimeter cubed. Determine the equilibrium concentrations of N2 and H2 and calculate the Kc value. So first step, as always, is write the reaction. It was written before, but I'm rewriting it. So N2 plus 3H2 gives us 2 NH3s. We need to set up our initial concentration, our change in concentration, and our concentration at equilibrium. We are starting with 0.20 moles of N2, 0.20 moles of H2, and 0.00 moles of NH3 because it's a product. We know we have 0.060 moles of NH3 at equilibrium. The rest of the information is unknown. So if we know that we have 2 NH3s and those 2 NH3s make 0.060, we know each individual one has 0.03 moles. So that means we need to subtract 0.03 moles from N2 and then subtract 3 times 0.03 moles from H2. Do this math, 0.20 minus 0.03, you get 0.17 and 0.11 moles per decimeter cubed for your two reactants. Then we already wrote the equilibrium expression, but I'm going to rewrite it since it's on a different page. Alright, substitute your information in. We have 0.06 squared over 0.17 times 0.11 cubed. Go through, plug this into your calculator. Be very careful with that cubed function that you're doing it properly and isolating it, but you get 15.9. This tells us that products are being favored. All right. So, using that information, predict and explain how increasing the temperature will increase the effect of Kc. The Haber process has a delta H of negative 93 kilojoules per mole. So it is an exothermic process. If we increase the temperature in an exothermic process, increasing temperature favors endothermic. Therefore, this is an exothermic process, we are going to favor the reverse direction or your reactants. And how will this affect the value of Kc? Well, when we favor the reactants, we decrease the number for Kc because reactants are on the bottom. Number 26. The reaction was studied at 550 degrees Celsius when 4.0 moles of carbon monoxide and 6.4 moles of water were introduced into a 1 decimeter cubed vessel. The equilibrium mixture was found to have 3.2 moles for both H2 and CO2. Calculate the concentrations of CO and H2O and the value of Kc. Let's rewrite our reaction. We need our initial concentration, our change in concentration, and our concentration at equilibrium. We know we have 4 moles of CO, 6.4 moles of water, 0 moles for each of our products. At equilibrium, we found we have 3.2 moles of both H2 and CO2. Since they are a 1-to-1 ratio, that means we had increased them each by 3.2. We need to subtract by 3.2 on our reactant side, and again, 1-to-1 ratio. Do the math. We get 0.8 and 3.2 as the concentrations for our reactants in moles per decimeter cubed. Then we want to find the value of Kc. So Kc equals products over reactants. We have no exponents because there are no coefficients. Plug in your numbers. 3.2 times 3.2 gives us 3.2 squared. So I'm just combining those. Plug this into your calculator and you get 4.0, which means that is the expression at equilibrium. As long as you change nothing else, everything at equilibrium will equal 4.0 for this reaction, which takes us to the second question. Of at the same temperature and pressure, so we are not changing anything else. We're keeping the same pressure and temperature, so same conditions. A different experiment was found to have 4.0 moles of both CO and H2O and 3 moles of H2 and CO2 present in the mixture after a period of reaction. Show mathematically that this mixture had not reached equilibrium and in which direction it will react. So again, I have already written our equilibrium expression, so I'm just going to input our new data. So Kc equals, we have 3.0 squared, because both our products are 3.0, and both of our reactants are 4.0 squared. Do the math, you get 0.56. That does not match this number. It is lower. So it does not equal the above Kc at equilibrium. Therefore, we need to increase the number for Kc. The way in which we need to do that is increase the amount of products in our reaction in order to match the equilibrium expression.